Okay. Hi, I'm Xuan. Thanks for your interest in our paper, Pyramid Recurrent Network for Predicting Crowdsourced Speech Quality Ratings of Real-World Signals. We are the research team from Indiana University, United States. The work was supervised by Professor Donald Williamson. Okay, let's begin. Speech can be assessed by using either subjective methods or objective methods. Subjective listening studies are the most reliable form of speech quality assessment for many applications. Listeners often rate the perceptual rating of testing materials using categorical or multi-stimuli rating protocols, such as A/B preference test or the Musha test. However, the cost and time-consuming nature of subjective studies hinders its applications. Computational objective measures enable low-cost and efficient speech quality assessment, where many intrusive, non-intrusive, and data-driven approaches have been developed. Intrusive methods such as the Pascal, SDR, and OCA generate quality scores by calculating the dissimilarities between a clean reference speed signal and its degraded counterpart. These measurements, however, require access to the original speech, and they don't always correlate well with subjective quality results. Non-intrusive metrics, on the other hand, assess speech based on the distorted signal only. They use signal processing concepts to generate quality assessment scores. Many non-intrusive measurements have been proposed in the literature, such as the HTOT standard P563, ANIC Plus, and SURMA. These approaches, however, rely on signal properties and assumptions that are not always realized in real-world environments. Hence, the assessment score are not always consistent with human ratings. Many recent work uses data-driven methods to estimate speech quality. Related works include the NISA, the Outliers, the Quality Night, DNA-based approach, and NISCLA. They use machine learning or deep learning models to extract features and then build the relationship between the spatial temporal representations of a speed signal and its quality scores. The motivation of our project is that we found the real-world capabilities of objective speech quality assessment are limited, since current measures predict objective scores that are not always strongly correlated with subjective rating in real-world environments. Since the usage of objective quality scores at training targets is a major limitation, because we know the objective measures only approximate human perception. And also we found a large dataset of real-world signals with listener quality ratings does not currently exist. So these are the reasons what have motivated our work. In this paper, we conducted a large-scale listening test on real-world data and collected 180,000 subjective quality ratings through Amazon's Mechanical Turk using two publicly available speech corpora. We additionally developed an encoder-decoder model with pyramid, bidirectional IST network, and attention mechanism to non-intrusively predict the perceived speech quality of these real-world signals. Okay, I will introduce each part in 10. Okay, firstly, let me introduce how listening studies are conducted. We created 700 human intelligence tasks on Connecticut for our crowdsourced subjective listening test. Each task was completed by 5 crowd workers, and also each task contains 15 trails of evaluations where we design the studies follow the recommendation of ITUR, the Mosha protocol. An illustration of evaluation trail is shown here. Each trail has multiple stimuli from varying conditions, including the hide and clean reference, the anchor signal, and multiple real-world noisy or reverberant speech signals. After listening to each signal, the participants are asked to rate the quality of each sound on a continuous scale from 0 to 100 using a set of sliders. We clarify the quality scale. So songs with excellent quality should be rated high, and bad quality songs should be rated low. Okay, let's talk about the speech material. Uh, we use two speech corpora that were recorded in a wide range of real-world environments. The cosine data set is a set of multiple party conversation recorded in real-world environments with background noise and interfering speakers. The voices data set was recorded by playing clean audio in rooms of different size. Each has a distinct room acoustic profile. Background noise was played concurrently, so the voices cover realistic, noisy, reverberant conditions. In the listening study, we deployed uh, 18,000 cosine signals and 18,000 voices signals. Each stimulus is truncated to be 3 to 6 seconds long. In total, 45 hours of speech signals are generated and 180,000 subjective human judgments are collected. Crowd workers' response are rejected if they don't meet some requirements, such as and also if their response contains malicious behavior or like the random scoring or the amount of unanswered response is maybe too much. Data cleaning is then performed to remove rating bias and the obvious outliers. We use 3 algorithms. They are the Z-score transformation, the DB scan, and isolation forest algorithm. A rescaling step is then performed to normalize the rating ranges amongst all crowd workers. We use the min-max normalization, and the new rating scale is from 0 to 10. After data cleaning is completed, the scaled ratings for each stimulus are averaged, and this is used as the noise for the corresponding signal. The full distribution of the scaled noise of each speech corpora for each condition is shown here. To predict the human quality ratings of real-world signals, we proposed a attention-based encoder-decoder model. Its architecture is shown here. This approach consists of encoder and decoder. The encoder utilizes stacked pyramid bidirectional LSTM layers to convert low-level speech signals into higher-level representations. The decoder is implemented as an intention layer followed by a fully connected layer. The decoder specifies a probability distribution over sequences of features using a self-tension mechanism. It is uh, it translates these higher level latent features into a alternate level quality score. We report four established measures for evaluating the performance of non-intrusive measures. They are the epsilon insensitive root mean square error, the mean absolute error, Pearson correlation coefficient, and Spearman rank correlation coefficient. We compare our model with six non-intrusive measures, including two conventional measures that are based on voice production and perception, the ITU P563 and thermal. And we also compare with four data-driven approaches that utilize deep learning. The, the optimal is consists of a stack of LSTM. The coordinate uses one bidirectional LSTM and two free connected layers. A DN-based approach that uses the multiple dense layers. NISCA uses a combination of convolutional neural network and bidirectional LSTM layers. Okay, let's take a look at the experimental results. The proposed model is denoted as P-LSTM plus the attention. As can be seen from the results in table, all data-driven approaches outperform the conventional measures with a good margin. When comparing to recent data-driven approaches, the proposed model achieves the highest performance in terms of both prediction error and correlation with the ground truth noise, except for the RCC of the DNA model on voices data. Our model also shows statistical significance against approaches and metrics, except for the ME and RMSE and the cosine data with NISCA. Okay, let me summarize our work. In this paper, we present a data-driven approach to evaluate speech quality by directly predicting human voice readings of real-world speech signals. A large-scale speech quality study is conducted using crowdsourcing to ensure that our prediction model performs accurately and robustly in real-world environments. Attention-based pyramid recurrent model is then trained to estimate noise. The results show that our model achieves statistically lower estimation errors than prior assessment approaches, where the predicted scores strongly correlated with human judgment. The collected dataset will be made available to facilitate further research efforts. Okay, this is the reference of the slide. Okay, thanks for your attention to our paper. For more information, please refer to our paper and website. Okay, thank you for your time.